Hi, everyone. Yeah. I don't know. I picked a very contentious topic, hoping there'll be a lot of energy in the room. Let's see how it goes. Yeah, okay. So, canonicalization in MLIR. So, first we'll cover the basics, and it's not a deep dive, so it's really going to be like, explain a little bit what's canonicalization in MLIR, how it's done, etc., so that everybody's on the same page. And then we'll talk about what's the problem with it. Then try to understand the problem from different perspectives and see if we, in the Q&A, reach some conclusions and consensus. So, okay, so what is canonical form and canonicalization? So basically, a canonical form is a rewrite of the IR at the same abstraction level as the original, but in simpler form. So, for example, you have a vector broadcast. You're broadcasting one value, really, 1 cross F32 to 8 cross 1, and then that value is transposed from 8 cross 1 to 1 cross 8. You can quickly see, like, okay, maybe it's easier and simpler if you could just broadcast that single value to 1 cross 8. And if you run the canonicalizer, that's what it's going to do. And so, okay, if you want to have something like this for your ops, what do you need to do? Okay, so in the table gen description of your op, so in this case, a transpose op, where you have defined your op, you say has canonicalizer equals to 1. And so then what happens is from the table gen backend will generate the class description of a declaration of your op. It will populate this get canonicalization pattern, which takes arguments, rewrite pattern set. Then what do you do in your implementation? So in this case, in your vector transpose op, get canonicalization patterns, you add those patterns. So for the example before, you add this full transpose scalar, it's kind of long name, as one of the patterns. And the code below it, you see, okay, what that pattern does really is a match and rewrite, where it gets a transpose op, and then it sees, okay, is my defining op, so the input to the transpose op, is it a broadcast? If that's the case, I'm going to just replace the transpose with the broadcast, basically to get back what you had below here, where the result is from the transpose and the source is from the source of the broadcast. I mean, the details of this doesn't matter. It's basically like, okay, there is a way of stitching together so you can get the canonicalizer to do and get you the code that you wanted, right? There is another way, which is using the DAC pattern matching. So suppose you have minus x divided by minus y. We know from basic arithmetic that's the same as x divided by y. And so you can rewrite this DAC pattern where the code in the gray is the pattern you're matching, and the one in blue is the rewrite. So basically replacing the operands, etc. So instead of doing the negatives of the two operands, you just straight away do the division. And so what happens is you write this DAC pattern, and the table gen backend, in which in this case is a rewrite gen.cpp, will auto-generate for you the code that we saw earlier with the match and rewrite. So it just builds a boilerplate code or whatever you call it in this case. So you get the job done with less code. So yeah, these are two ways, and another is the fold patterns that you can write. And actually for a lot of the arithmetic and math thing, the fold is much more the preferred way for a lot of folks. This talk is not about how really to write the canonicalizer patterns, etc. There's lots of write-ups on this. So this is just so that everybody understands, okay, this is what's really we're talking about. You might have used it a lot in the parsers that you build. So for example, if this is a piece of code which is kind of like, it's got a lot of things in there for a purpose because I want to show how it gets cleaned up. So in this case, you have a linear generic which gets a bunch of inputs. Those are dynamic shapes. And it wants to create a tensor empty. It needs the sizes. So therefore, it probes and gets the tensor.dim, etc. But what's really happening inside the generic is yielding back the inputs that it got in the reverse order. And if you run the canonicalizer, this is a much better code, isn't it? Yeah? OK, so that's great. Talk is over. That's what the canonicalizer does. What's the problem? Well, if you've been following the RFCs and the diffs, well, this is a very contentious topic. Why? Because simple forms are easy. OK, you rewrite it, you get smaller code, and most people agree on certain things. But look at the example on the left. You got a transpose. You're transposing a 1 cross 5 to a 5 cross 1. You could get the same effect if you did a tensor cast shape. Shape cast, sorry. Yeah? OK, yeah. On the right-hand side is a more complicated example. So you're doing an insert slice. You're inserting something into something, which is essentially overwriting the destination tensor. You get a new tensor, of course, and you could get the same thing if you did an expand slice of the original slice. Now, which one is the more canonical form? And there's lots of debates about this because it depends. Let's say you're looking for a pattern, insert and extract slice. You prefer the first one. If you're looking at it from a different perspective, you say, OK, expand shape. I want this to be rewritten. So it's back and forth. OK, and as in the bottom you see Matthias. There, has identified like, OK, these are two examples, but there are a lot more actually. We have been having these debates again and again about like, which is the canonical form. So there you go. That's a can of worms. I've not opened it because we just had lunch, so you don't want to feel messy. OK, what are the problems? Define the canonical form. This side of the room has one definition. That side of the room has another definition. For a particular case, what is a simple canonical form? And then most people say, oh, there's no canonical form. Is it canonical or optimization? Which one is better on all this? Are you making it better or worse? How come your past is relying on a canonicalizer, which is not supposed to be the case? OK, it's good, but it's taking too long because everything under the sun has been put under the canonicalizer. Right? So, OK, maybe we can step back and say, like, OK, let's get some actions, yeah? So eliminating operations is a good idea. So suppose like x plus 0 is x. You can think of it in terms of like a linear generic. With a linear generic, just takes the inputs and forwards it to the output. Basically it's a no-op where you can fold them together. And at different instance level, you can start thinking of, oh, what's the identity? What's the inverse, x and x inverse? And those can be folded. Or permutations, if you're doing a transpose followed by a transpose, I can fold it, etc. Or canonicalize towards fewer values. Now, as it gets trickier, fewer values may not always mean better, right? But if you're thinking one way, if you're passing x and x, just pass x. Let the op, you have a new op, a different op that can do that. Reduce the variety in the code. So, yeah, one of the things that you really want in your canonicalizer is reduce the variety, and that's because then your passes which you write using it can only cater or address a particular style of code. OK, are we veering quickly down to like, we want the code into a very compact form? It's like homograph complexity. We want it in a very compact form. And no, because if you think about it, like for most people would know LLVM, and like if you see the canonical form of a loop, you have a pre-header and a loop exit. You might not be compressing it. Actually, you're rewriting it in a form that is much more amenable for other things, like hoisting some code, etc. So compact is not the same as simple. And so what is it then? OK, let's take a step back then. OK, what is canonical form? We are not the ones who invented this word, right? So it comes from mathematics, computer science in general. So what do they mean there? Maybe just using the wrong word or using the right word, but very loose about the definition. OK, so canonical form is the unique representation of an abstract object. Abstract could be an op or an integer, etc. So uniqueness is important. And that uniqueness comes from some mathematical property, and it's okay. And you have this unique canonical form, but everything needs to be translatable to it, otherwise no point. So that's the closure part. And then if two things, their canonical form is the same, that means we have to agree that they are the same. And all these things help build transformations, optimizations, query, that once if we agree, okay, this is the canonical form, then we can do that. Now, so, okay, I should have shown this one. So two properties, like, we abstract away, even from, okay, whether it's an op or an integer or whatever field, canonical means like, if once you do the canonical form, you get something, and if you run it again, whether it's an op or an IR, you don't get something else, convergence. Yeah, and the other one is equivalence, like, if two things, canonical representation is the same, then we have to agree that they are essentially the same. What essentially is happening, like if you think in terms of IR, you've got this one IR and you can rewrite it in 10 different ways. You're trying to find that unique thing where, okay, that's the canonical form of it. And that depends on context, because what is the representation? So take an example like, okay, so we know, okay, any number greater than n can be represented in one way using prime number. That's a fundamental theorem of arithmetic. What's the context? You want to represent it as multiplication. The same number 1,000, I think it's 10,000, yeah, in this case. You can represent 1 plus 1 plus 1 plus 1. That's also canonical, unique, but that's a different context. So context matters. Oops, what's this? Yeah. And actually, we have seen canonical forms in many different disciplines. And so it's nothing new in MLIR. I mean, we have adopted it very good, I think, in that way. So whether you're doing the, finding the basis vector by reduced echelon matrix or all the different discipline, canonical form has helped. So what are we missing here? Why, when it comes to op and IR, it doesn't seem to help us? Because if you really think about it, what is it that we're looking for? We are looking for orthogonality, meaning, like if you have an op doing something, that op should not be able to do the same thing in 10 different ways. Now, for ops, that's pretty easy, but when you have a bunch of IR, a bunch of ops, if you can rewrite in 10 different ways, then you don't have a canonical form. So you have competing simple forms of IR. Just to dig in a little bit more on that, so for an op, it's easy. By definition, there's only one way to write arith.add. Okay, it's canonical by construction. If you have a generic op, linear generic, then maybe it has unused arguments that you can throw away, or default map is actually an iterative map you can also throw away. And at the construction, you can create something that's, you can say, is canonical. But then when you come to a bunch of ops in your dialect, if you have two ops competing with each other that are essentially the same, then you run into this problem. And so that's the root of this problem, okay? So therefore, there's been a lot of discussion on this. I'm just trying to bring to the audience all the different perspectives. I'll run through a little bit. So op has a canonical form either in general, which is hard, per pass, per phase. So the more contextual you make it, you have more agreement. Okay, this is what you're doing. Okay, this is my canonical representation. The generic, so at a higher level of abstractions, like a linear generic, it's harder to agree on a canonical form. At lower abstraction level, because it just does a little small thing, maybe it's easy. Some would view canonicalization really as a pre-processing, basically things you do for your pass or set of passes. A generic, a big one, a global catch-all is not really. And then I have more examples of it. Canonicalization should not be required for correctness, should not semantics, etc. Okay, let's see. So as canonicalization is often run, should not be too computationally intensive. So these are some sort of axioms people things that people agree with. Should not be required for correctness. Bar for something in the canonicalization should be high, meaning not anything and everything. And avoid cycles, meaning if we have designed the whole IR such that there are many competing ops at the same doing essentially the same things, you have these problems. So this is part one, so my perspective. So aspiring for a canonical form is not realistic. Overlapping ops do exist. There's a reality. What we can view is the canonicalizer really as a simplifier. It helps me. I mean, I run it, I see, oh, the code has become smaller. Yeah? So it reduces clutter, the folds, etc. Keep it thin, or restructure it for different context. So it's not me just throwing my opinion on you. Let's have a poll. First question, should canonicalizer be removed? If you raise your hand, okay. Should it be retained as is? Raise your hand if you agree. Okay, we got, okay, so 2 hands. So first one, should it be improved? Yeah, more hands. Of course, we love improvements. And now we have the arguments. How should it be improved? Should it have levels like optimizations or restructured? This is an idea, actually Mahesh gave it to me. Restructure it for a more like contextual. So we haven't ironed out how exactly to go about it, but I think I think most people would like it, and in the Q&A we can discuss more about it. So the point of this was not really to present like a tutorial on canonicalizer. We want MLIR, like how Alex was saying this morning, things to improve. Don't just accept everything as is. So this is a great thing. We want the canonicalizer to do things better. We find it useful, and sometimes we find it very annoying because it destroys things. So how we can improve MLIR, and so this is the point of this presentation. Do you want to have more polls? Okay, so here is a bit cast. So you go bit cast from A to B, and then B to C. You can go straight from A to C. Do you think this is part of canonicalizer? Should it be? Show of hands. Yes, yes, yes. Okay, 4 hands. It gets harder. This one. Do you want this code to be cleaned up? Yeah, I guess most people would agree. Yeah. Okay, in this case, you have a tensor of 0 size. It's inserted. So basically, the insertion is NOP. Or you have a tensor overwriting the whole destination. Yes, is this canonicalizer or is it optimization? Canonicalizer? Yeah, yeah, most people. So there are people who like the canonicalizer. How about this one? So you go from to tensor, and so you go from memref to tensor and tensor to memref. The top one. Yeah, show hands, yes. Yeah, okay, thank you. Few hands. The second one is you're going from memref to tensor and tensor to memref, but you're going across address space. So what the canonicalizer does is it actually does an alloc memref copy. Do you want that? Yes? Hands? No? Okay. Anyway, Q&A. This one propagates the shape. So you go from a fixed shape to a dynamic shape, and then you have a lineage. But actually, if you run the canonicalizer, it figures out that one of the dimensions is actually not truly dynamic. It's been propagated. The point is, if you didn't run the canonicalizer and your parsers were all interpreting that everything as dynamic, you have suboptimal code, isn't it? So we need these solutions, but what's the best way to get these solutions is what needs discussions. Here's another one. Okay, I need really hand. So you go from BF16 to F32, you do a math operation, then you go put the result back to BF16, you do a sign, and what the canonicalizer does is it just does the conversion from BF16 to F32, does the 2 math absolute and sign, and then gives you back the result. I think that's cool, but that's contentious probably, yeah? Do you want it? Is this canonicalizer? Assuming it's correct, like what it's doing. Yeah? Okay. Anyway, this is a contentious issue, so I want to leave more time for the Q&A. So I finished 1 minute before. Hopefully you won't take it away from me. So yeah, thank you.
Thank you, Javed, for a great talk.
Thank you.
Questions, please.
And I don't have the answer. Matthias has answer. Where is Mahesh?
I'm here.
Hi, thanks for the talk. So since you brought up the connection to
other disciplines. In sort of term rewriting contexts, a very common property you want is that you have confluence. So no matter which order you apply canonicalization patterns, you should get to the same place. As far as I know, there's no sort of requirement on MLIR patterns to have this property in any way. Is this something you believe they should have? Is it something we could even want to have if, is it something that's even achievable if we wanted to have this?
Could you rephrase the question? I don't know if I really...
So a common thing you want with these sort of rewriting systems and the sort of theoretical background between them is if I have two different rewrite patterns on, say, two different operations, it shouldn't matter in which order I apply them, I should be able to get back to the same canonical form no matter what choice I took.
The reality is that's not true when you have a large IR.
I agree that's probably not true at the moment, but is it seen as a bug when this doesn't hold? Is it something people want to strive towards? This is a bit of an open-ended question. But.
Maybe.
I don't know how you would enforce that. Patterns can do whatever they want, and it's very hard to, even if that's happening, it's very hard to find cases, how to trigger it, how to test it.
But maybe, how to enforce it even.
Yeah, enforce it, but maybe it sounds like a useful property.
Yeah, I think the property is useful. But yeah, okay.
Can I add to that?
Yeah.
I think on that part, we just need a way to randomize the order in which the patterns are applied. That should be a test in tree.
True.
Well, yeah, sure, but also like mathematically, there's a theorem that says local confluence plus some other property implies confluence. So I do formal proofs, and in the context of a proof assistant, right? It's like we also struggle with this because when you write down a theorem, there are many ways to state the theorem. So it's important to have normal forms. And so we have a linter, which essentially, so the idea is that if you have like many rewrites, what you can do is to like construct a synthetic term and then apply rewrite A and then rewrite B and then rewrite B and then rewrite A. So essentially you can show that like if all such diamonds give you the same answer, then the full rewrite system will give you like a canonical normal form.
That's very close to what Mahesh was saying.
But sort of instead of like randomizing the orders, you can actually like you can write a program that like you can algorithmically test this property. So it doesn't need to be like a test. You can sort of like you can write an algorithm that checks this. I'd be happy to chat with people if they want to discuss.
This is what it's for. Yeah. So consensus seems to be people. I mean, from the show of hands, and of course this is not fully represented. People do find the canonicalizer useful. What is that in your strong opinion on it should be removed and everybody fends for themselves?
So I have an answer to the post question.
Yeah.
I think we already kind of accepted that MLIR is chaos, and I think it will always be chaos. And while Siddharth can do formal proofs, us mere mortals, we write wrong shit all the time. And I think ultimately what we need is just a way to customize it.
Yeah.
I need different flavors of canonicalizer. It's never all going to fit into one box. And right now I have to opt into all canonicalizations or no canonicalizations, or I have to copy paste the upstream canonicalizer.
Exactly.
I just want it to be extensible somehow.
True. Yeah, we should fix. I don't know. My opinion is we should improve it, but not remove it. But yes.
But I think that's exactly the thing, right? It's like it seems to be one system, but it's used for so many different things currently, right? There's like a canonical form, unclear what that is. We do like simplification, like avoiding computation that like folding stuff. And sometimes we just use it as like to enable preconditions of passes or something. So maybe we should kind of make this explicit that there are different things we use it for, and then have like one thing which folds stuff, but other things where you can say like, my pass has these preconditions on the IR, and you can kind of make that explicit, formalize it somehow as like a normal form or something.
Yeah.
I just think it's super important to not formalize it, because as soon as you... The problem is, as soon as you put it into these strict boxes, then people will just get it wrong all the time, and then you will end up having all these fights about what belongs where and what doesn't belong where. Mm-hmm. And I think that is nice to have the option to do that, but we should also have the option to do pretty much whatever. That's why it needs to be extensible. Not just 2 levels or 3 levels. We really need like a downstream extensible way of working with.
So Sid, you can do the work, but keep it in your repo and never commit it.
Both, depending on the use case, right?
Yeah.
But that's kind of what I mean, right? Like a pass can declare, I need these specific canonicalizations. So you opt into those. These are the preconditions for your passing, right? So it needs to be more flexible. That's what I think.
Yeah. Matthias?
Yeah, maybe one comment to that. The pass could also run these canonicalization patterns itself. But there was another point I wanted to bring up. I'm not sure if people are aware, but if you use the canonicalizer pass, right now you have the problem that it may just suddenly stop. So it's based on a greedy rewrite, and there's this basically check. If we do too many iterations, we notice there's too much work to do, we just suddenly stop. So even if you have this idea of a canonical form, you have decided what it is. Right now, we don't necessarily reach it. You might just stop suddenly, and the pass doesn't even signal a pass failure. So that was something that was discussed on an RFC. So unfortunately, we couldn't find consensus there. But maybe that for me personally, that would be one thing where we could start improving the canonicalizer.
Why doesn't it give the partial result as okay, take it as it is?
Say again?
So can it give a partial result? Like, I've half-baked cake?
Yeah, I mean, it starts rewriting the AR, and then it will just suddenly stop. And then you, as a programmer, you don't really know, did I reach that canonical form? It's just, okay, half of it is done, half is not, because it took too long, and you don't even get the result from the pass. It just says, okay, pass succeeded, but it's not really in canonical form. So for that's why I voted for maybe let's delete it. Because
and I wonder, it's not like, dialect conversion where half, it's not as good, because if it, but
so,
in this case, half is okay, maybe.
Yeah, but then what is really, is there any kind of post condition? What kind of post condition holds after the canonicalizer? You can't really say it's in a canonical form. You really don't know. Maybe nothing happened. Maybe there was a pattern which went into an infinite loop. Well, we tried a few times, and then eventually we noticed, okay, this takes too long, we just stop. So you have no idea in what state the IR is afterwards. Yeah, just random comment.
And to add to Matthias' point.
And that would be the last question.
I'm just going
get the last say.
add to his point, because it came up with during lunch. So if somebody adds a pattern to another dialect that just gets pulled into your canonicalizer, your compiler behavior changes, even though nothing that you are using changes, because it just happened to run a pattern that was added completely out of band. So it's completely non-deterministic, not controllable. So definitely canonicalizer as it exists today is broken. We need to fix it, but I agree there are a lot of different solutions.
Thank you.
Thank you. Thank you, Jared, for the great talk and triggering wonderful discussion.